I remember in college, I once took this class around number systems and binary logic, and instead of being a normal person and taking down notes like everyone else, I recreated the entirety of whatever was going on inside of that class in Minecraft like an autist. The cool thing about Minecraft is you can build actual functioning circuits from just the redstone mechanics in the game. So people have built actual computers and registers and CPU registers and all of that stuff all just inside Minecraft. So it actually serves as a very good educational source. And if you stick around for the entirety of this video, I'll show you exactly how it's done. Damn, I haven't played this game in ages. But yeah, I heard the new Minecraft movie came out or something, so that just reminded me, oh yeah, I should make something based around Minecraft. But yeah, no, we'll get straight into it. So I guess the first part of understanding, like, what is, like, if you've ever heard of a one or a zero in computers or programming, all a one or zero is it's a state of being like true or false. So that can be replicated inside of a computer system by just giving an on signal and an off signal. So that's all binary is it just means on or off inside of computing. And that's how an actual computer works, is you have a bunch of these kind of like on and off switches, and based off of that you can build bigger kind of systems off of just like the on or off state inside of like a transistor, let's say. But yeah, Minecraft, you can just replicate that with like redstone or anything else. So just an on or an off thing. So once you've got that out of the way, well, you could also describe this as a single bit. So a single bit is just one on and one off. And in binary, it's just written down as a 1 for on, and then a 0 for off. So once you get more complex kind of systems, those are made up of multiple bits. So multiple things that are on or off, or it could be on and on again, and then it could be off and off again. And that's how information is stored inside of a computer. It's just you have millions of these kind of on or off states, which are then used to interpret further data. And, you know, like one of these, like let's say if it's just a 1, that's 1 bit of information. So it's not too hard to understand, I hope. But if you zoom out in a larger scale, you have loads of these, and those give you more logic. But yeah, I guess I'll move on to the next part, expanding upon that. So this section looks a bit more complicated. You have multiple like different kind of different sources of information here. So you've got one you've got one bit here, you've got one bit there, and if you add all of these up, so 1, 2, 3, 4, 5, 6, 7, 8, that gives you 8 different bits. And if you've ever heard of the word byte before, like 1 byte, 8 bits are equal to 1 byte of information. So you can also notice, like, you know, what is a gigabyte? It's probably like, I forget the exact number, but it's, wait, let's actually search it up. How many bytes in a gigabyte? So yeah, 1 to the power of 9. That's quite a lot. But you can kind of get the idea, like that, you know, like it's kind of impractical to say the exact number of something. So it's kind of like being metaphored as in like 8 bits or 1 byte, and you can expand upon that. So yeah, that covers what bytes are. Now if you're looking at this, you're kind of wondering to yourself, like, how the hell do these make up actual decimal numbers, like the numbers that we're up to? Because you can see if you start counting here, you're just going to see 0, 0, 1, 1, 1 0 1 0. So how does that actually translate into decimal? Well, it's actually there's a thing called positional notation, and that's essentially how we translate numbers from, or that's kind of like the basis of how we translate numbers from binary into decimal and to other different number systems. So we'll actually go ahead and we'll start calculating, or like calculating how binary systems get translated into decimal systems. So if we start off here, we can see at this place we start. I named this 0th place just to make it easier for you to learn. So this is going to become 2 to the power of 0, and the reason why it's 0 is because to translate these into decimal, you have to get like since in binary you only have two states, you have a true or a false. The base of the kind of exponent is going to be 2. So you have 2 to the power of 0 here, you have 2 to the power of 1 here, 2 to the power of 2 here. You basically kind of I'll show you how it's done. So you only want to calculate the place, or like, you know, what 2 to the power of it is it, like in just places that have the on signal. You don't want to do it for places that don't have a 1, essentially. So this is going to be 0 0. You do not calculate for that. You only want to calculate it calculate the kind of power thingy in places that have the on signal. So it's a bit confusing at the start to grab your head through, but I'll explain it step by step. So over here you have 2 to the power of 2, and then that gives you 4, and then 2 to the power of 3, that gives you 8, 2 to the power, get out of the way, 2 to the power of 4, I think that's 16, let me just check. Yeah, that's 16. 2 to the power of 6. Wait, I have to calculate that. Yeah, 64. So basically, when you've kind of calculated this for each kind of place it's in, then all you have to do is, wait, did I calculate 2 to the power of 4? Yeah, that's 16. I forgot to write it down. Oops. But yeah, once you have a kind of calculation at each kind of place, then all you do is add them up together. So we'll just go ahead and do that. So the first number is 4. 4 plus 8. 4 plus 8 plus 16, I think. Yeah, plus 16 plus 64. So then you have the number 92 in decimal. And we can kind of confirm this by just like kind of typing it into Google. What is, so I'm just going to type in what is 0 1 0 1 1 1 and then 0 0 in or binary to decimal. Yeah, we'll use that. So we can see we got the same answer. We got 92 once we added all of these numbers up. And the reason why that works is because you're working with the base number of 2, and then these are how it's represented in binary. So the further you go to the left, the higher the power gets. So you can imagine like it starts from the left at 0 1 0 1 1 1 1 0 0. It gets increasingly more powers as you go left, and it decrements in power as you go right. So I hope that gives you a kind of low level understanding of how like numbers get translated inside of, you know, computers and the sort of logic that goes behind it. And we could go a step further and we could, like, you know, figure out how these are represented in hexadecimal, because hexadecimal is a number you're probably going to see a lot, especially if you've watched like my reverse engineering kind of series. You're going to be kind of translating between hexadecimal and hexadecimal and decimal, and sort of seeing how all of those are interlinked. So, I guess I'll just do one more, which is translating from binary into hex. So, from binary into hex, I guess we'll first like write it down. So 0 1 0 1 1 1 0 0. I think it's 0 0. Yeah, and then what you want to do in hex is basically you want to group these in pairs of 4. So instead of, well, I'm just gonna write it down here. So instead of like that whole big string, you just go 0 1 0 1, and then you do 1 1 0 0. And basically what you do then is you calculate, you do the exact same thing here, in which you calculate in powers of 2. So in powers of 2, that's 2 to the power of 0, 2 to the power of 0 plus 2 to the power of 0 1 2. So that the first part is going to be equal to 5, and then we get the ones on the left. So 2 0 2 1 2 2, 2 2 plus 2 3. So we get 12 there, or 12 in hexadecimal. So basically, whenever you reach the number of 10, you start representing it with letters in alphabetical order. So 10 is A, 11 is B, and then 12 is C. And so we should get the output. Wait, 0 1 0 1. I think 5C. Maybe the ordering is going to be wrong, but let's just search it up here. So what is 92 in hexadecimal? So yeah, it's 5C. So that's the way it works there. It's very easy to translate numbers from hexadecimal into binary, because I think it has something to do with it's divisible by that number. And when you're doing it in decimal, like, since it's 10 and it doesn't divide that easily, well, I think my logic could be wrong there, but yeah, no, it's easy enough to translate from binary into hexadecimal. There's also different number systems. I think there's the octal number system. I'm not really going to do a practical example for that, because like the ones you see most commonly are just decimal and hexadecimal, and you know, then there's the binary kind of underneath that. Like, once you understand these three, you kind of understand them all, so there's no reason for me to go through them. I'll also be covering how to do logic gates inside of Minecraft as well. So if you saw inside of like the previous reverse engineering tutorial, I had stuff like logic gates, like XOR gates. If you ever saw the kind of XOR operator, which was like 30 XOR 20 example, I'll teach you how to do that shit inside of Minecraft, because you can do it. and it gives you a better visualization. But I think that's all I have for this one. So bye.